Welcome to the 8th lecture of the NPTEL MOOC on parallel algorithms. In the previous class, we were discussing the algorithm design technique called divide and conquer, in which a given problem is divided into several subproblems. The subproblems are solved in turn and then their solutions are combined to get the solution for the given problem. So, we have seen a couple of examples of divide and conquer. We shall see more problems that can be solved using divide and conquer today, but before that, one particular problem that we will be using as a subroutine, which is the problem of searching. Let us say we are given a sorted array of size n and we have an element x. We want to find if the element is present in the array or not. And if the element x is present in the array, what is its rank? The rank of an element in a sorted array is the number of elements in the sorted array that are smaller than or equal to the given element. So, we want to find the number of elements less than or equal to x in the given sorted array. So, we have the sorted array A of size n and an item x. We want to find the rank R of x in A. Let us say the model is CREWPRAM. So, we initialize R to 0 and then we do in parallel for I varying from 1 to n minus 1. That is, let us assume that we have one processor for every single element in the array except the last. So, we assume there is a processor stationed at every single element except the last. What these processors do is this: each processor is standing on an item I. So, the processor will compare x with AI as well as AI plus 1, that is the item on which it is standing and as well as the item to the right. If x is greater than or equal to the item on which it stands and is less than the item that is to its right, then x will have to fall between these two, that is between the item on which the processor stands and the next item. Then the processor will report I as the rank of x. So, it is like this: we have a number of elements and the processors are standing on each element. This one particular processor finds that x is greater than or equal to this element and less than or equal to the next element, which means x falls between the third and the fourth elements in this figure. In that case, this processor, the third processor, will report I as its index, which is 3, as the result. So, what it means is that the element x falls within the third segment. We assume that the sorted array divides the real line into a number of segments. So, the element that we want falls between the third element and the fourth element. If x does not fall between any two of the given elements, that is, if x falls to the left of the leftmost element, then R will retain its initial value, which is 0. So, you can see that the algorithm works correctly provided we have n minus 1 processors. With n minus 1 processors, the algorithm runs in order of 1 time. So, here we have assumed that the model is CREW, but where did we use the concurrent read? If you look at the code, you would not think that concurrent read is being used anywhere, because the access to AI and AI plus 1, since they are synchronized, will never cause a read conflict. When the ith processor is accessing AI, the I plus first processor is accessing AI plus 1. Later, when the ith processor is accessing ai plus 1, the I plus first processor is accessing the ai plus second element, I plus second element. Therefore, there will be no read conflict. But CREW model is necessary because X is not known to all initially. So, if all the processors have to read X simultaneously, we will require concurrent read. But if X is known only to one processor and this has to be broadcast over the other processors, then that would require order of login time on the ER-EW PRAM. Therefore, if this has to be executed on the ER-EW PRAM, it would take order of login time. If X is not known to every single processor to begin with. For now, let us continue with the CREW PRAM model. Let us say how we would execute search when we have P processors. So, we are going to generalize this algorithm. Let us say we have P less than or equal to n minus 1 processors. In particular, when we have only one processor, which is the sequential case, we know we would use binary search. In binary search, we look at an array of size n and then first we look at the midpoint. X is compared with the element in the middle. If X is smaller than the midpoint, then we will continue with the left side, otherwise we will continue with the right side. So, after every comparison, the search space reduces by a factor of 2. Therefore, if we are starting with n elements to begin with, in log n steps, the search space will reduce to one single element. Therefore, the algorithm will run in order of log n time. This is the sequential algorithm. So, now we have two algorithms representing the two extremes. If we have one processor, we will be able to perform the search in order of log n time. If we have n minus 1 processors, we will be able to perform the search in order 1 time. What if we have P processors where P is less than or equal to n minus 1? Then obviously we should be somewhere between the two extremes. So, can we design an algorithm which generalizes to the two extremes? Such an algorithm can be designed like this. Let us say we are given an array of size n and we have P processors. Let us say we divide the array into P plus 1 segments. So, in this case P is 5 and there are 6 segments. 6 segments correspond to 5 sentinels. So, let me call these the sentinels, they separate the segments. So, there are 5 segment separation points and therefore, in this example we assume that P equal to 5. So, we have 5 processors. What we do is this, we depute these 5 processors to these positions. This is the generalization of the binary search, in that in the case of binary search we have one processor and we send the processor to the middle of the array. Here we have 5 processors. So, what we do is to divide the array into 6 segments and send the processors to the segment separations. There are 5 segment separations. So, at these points we compare the element that is present with X. So, X is compared with all these positions. We assume that every processor knows X. So, our concurrent read has ensured that every processor knows X a priori, and then X is compared with all these elements. Let us say X is found to fall within this segment. That is, x is greater than or equal to the element with which P2 compares it, but less than the element with which P3 compares it. Therefore, we should continue with the search using the segment between 2 and 3, which means the range of search has now reduced from n to n by p plus 1. Initially, we had n elements. We divided these elements, n elements, into p plus 1 segments. Now we have reduced the search space to one such segment. The size of the segment is n by p plus 1 ceiling. So, in order one time, we have managed to reduce the problem size from n to n by p plus 1. This is analogous to what we do in binary search. In binary search, we reduce the search space from a size of n to a size of n by 2 in one single step. So, continuing like this, we find that the search can be executed in order of log n to the base p plus 1. After one step, the search space reduces by a factor of p plus 1. After two steps, the search space has reduced by a factor of p plus 1 squared, and so on. So, after log of n to the base p plus 1 steps, the search space has reduced to a size of 1. So, on the CR-EWP RAM with p plus 1 processors, we can perform the search in order of log n to the base log of p plus 1 time. This is, recall, is the same as log n divided by log of p plus 1, where the base of the logarithm is 2. So, let us look at a formal specification of the algorithm. When the input is a sorted array A and we have to search for an item x, and P is the number of processors, where we want to find the rank R of x in A, we proceed as below. When n is less than or equal to p plus 1, that is, the number of elements is less than or equal to the number of processors, then we use the first algorithm. That is, we can perform the search in order one time. Otherwise, we divide the array into p plus 1 segments, and then at each segment separation point, so I multiplied by ceiling of n by p plus 1 for each I varying from 1 to p is one such segment separation point. At each segment separation point, we compare x with the point. If x is greater than or equal to that, then we set the bi value of that to 0, otherwise we set the bi value of that to 1. So, what happens is this: here we have an array of size n. Let us say the element falls within this segment. Then how would the b values be? B of 0 is 0 and b of p plus 1 is 1. At all these positions we will have 0, here we have 1, here we have 1, and here we have 1. So, we find that the segment which contains the element corresponds to the switch from 0 to 1. So, for I varying from 0 to p, if in parallel we check this, if bi is 0 and bi plus 1 is 1, then we can declare the result as I plus 1. And then we have to confine ourselves to this segment that we have found. So, we recursively invoke search 2 on this segment, the reduced segment, which will give us the offset within the segment of x. That offset has to be added to r minus 1 times ceiling of n by p plus 1, which is the total of this length. The sum then would be the rank of x within the array. So, if x has been found to be within this and the offset is somewhere here, then the sum of these will be the rank of x within the array R. So, this is a recursively specified algorithm. Outside of the recursion, the time taken is order 1, but from one recursive call to the next, the size of the problem reduces by a factor of p plus 1. Therefore, the depth of the recursion is log of n to the base p plus 1 when we start with n elements. Since at each level of the recursion we spend order 1 time, the total time taken by the algorithm is log n to the base p plus 1. So, we can see that the two algorithms binary search, where we use one processor, and therefore, the running time is order of log n to the base 1 plus 1, and the n minus 1 processor search, which runs in order of 1 time, are both generalizations of the algorithm we have seen, where we use P processors and the algorithm runs in order of log n to the base p plus 1 time. The model used is the CR-EWP-RAM. We require the concurrent read because every processor should read the item to be searched x simultaneously. If we do not assume that every processor has a knowledge of x, then we can broadcast x over the processors, which would take an additional log of p time with p processors. So, on ER-EWP-RAM, this algorithm can be simulated in order of log p plus log of n to the base p plus 1 time. Now that we have seen an algorithm for searching, we will try to solve the problem of cross ranking. In cross ranking, we are given two sorted arrays and we want to cross rank the two arrays. To define the problem, first let me define the notion of a rank. The rank of an element x in a sorted array A is the number of elements in A that are less than or equal to x. So, by cross ranking of two arrays, two sorted arrays A and B, what we mean is that find the rank of every element in A in B and vice versa. For example, let us say we are given these two arrays. This is a sorted array, an array of alphabets. This is another sorted array. Let us say we want to cross rank the two arrays. Consider the element A in the first array. The number of elements less than or equal to A in the other array is 0. Similarly, D has no smaller element in the other array. Therefore, the cross rank of D is also 0. And the cross rank of G is 1 because F is the only smaller element in the other array. X and Y have cross ranks of 5 and 5 respectively. That is because all the elements in the other array are smaller than X and Y. On the other side, when I consider element F, we find that A and D are smaller than F. So, F has a cross rank of 2. J has a cross rank of 3 because A, D, G are smaller than J and X and Y are larger. L, M, N all have cross ranks of 3 because A, D, G are smaller than all of them. So, these are the cross ranks of the two arrays shown in the diagram. So, let us say we want to find the cross ranks of the two arrays. So, this is the algorithm for that. We are given two sorted arrays A and B of sizes m and n respectively. Let us say n is greater than or equal to m, this should be m, and we are interested in finding the cross ranks of A and B. So, the cross ranks will be given in arrays alpha and beta. Alpha will be of size m and beta will be of size n. Let us say the model is CREWPRAM. So, what we do is this: first, in parallel, for every element of A, we search for an element of A within B, and then for every element of B, in turn we search within A. So, in the first step we have assumed that we have one processor for every element of A, and in the second step we assume that we have one processor for every element of B. So, we have two Pardo steps, both of them executing in order of log n time. So, here we are in the first step we are searching within an array of size m. So, this will take order of log m time. In the second step we are searching within an array of size n. So, this will take order of log m time, log n time. So, together the algorithm takes order of log n time if we have n plus m processors. So, what it means is that the cross ranks can be found in order of log n time using m plus n processors, where m and n are the total number of elements. By the way, here we have assumed that B is of size m and A is of size n. So, cross ranking can be done in order of log n time using or m plus n processors. Now, let us see how to perform a merge of two sorted arrays. Let us consider the same two arrays that we have seen just now for cross ranking, that have elements a, d, g, x and y in one array, f, j, l, m, n in the other array. We had found these cross ranks. Element A knows that it is the first element in its own array, element D knows that it is the second element in its own array, and so on. So, every element has its own rank, its rank in its own array. Similarly, f, j, l, m, n respectively know that they are at positions 1, 2, 3, 4, 5 in their own array. So, in particular, consider the element, the third element in the top array, which is G. G knows that its cross rank in the other array is 1, which means one element is less than G in the other array, and 3 elements are less than or equal to G in the first array. Put together, there are 4 elements that are less than or equal to G in the two arrays together. So, if we add the rank of an element in its own array with the cross rank, we will get these values: 3 plus 1 equal to 4, 4 plus 5 is 9, 5 plus 5 is 10. And on the other side we have 3, 3 plus 2 5, 3 plus 3 6, 3 plus 4 7, 3 plus 5 8. So, this way we have found the rank of every single element in the output array. The rank of an element in the merged output array, in the output array every element should appear in sorted order. The rank of an element in the output array will be the cross rank added to its own index within the array. In particular, for element G, the cross rank is 1, which is the number of elements less than or equal to G in the other array, and its own rank is 3, which means at most 3 elements are less than or equal to G in its own array. 3 elements are less than or equal to G in its own array. So, the total number of elements less than or equal to G in the sorted array is going to be 4. Therefore, G should occupy the 4th position in the sorted array. So, every processor sitting on every single element in these two arrays now know which position it should occupy in the final sorted array. So, likewise, so accordingly, if we take 10 positions, if we take an array of size 10 in which we are going to write the output, G knows that it should occupy the 4th position. Likewise, A knows that it should occupy the 1st position, D knows that it should occupy the 2nd position, X and Y know that they should occupy the last 2 positions. Then the remaining positions will be occupied by F, J, L, M, N, and the array will be sorted. So, cross ranking is essentially equivalent to merging two arrays. So, now let us look at the code for this. We are given two sorted arrays A and B of sizes n and m respectively. Let us say n is greater than or equal to m. Our goal is to merge them. The output has to be written in an array C, which is of size m plus n, and the model is CR-EWP-RAM. So, in the first step, we cross rank A and B with the cross ranks stored in arrays alpha and beta respectively. Then we have two steps. In the first parallel step, every element of A will be copied into the corresponding element of C. The ith element of A knows that it is greater than or equal to I elements in A, and its cross rank is alpha I, which means it has at most it has exactly alpha I elements less than or equal to that in the other array, namely B. Therefore, its position in the final array is going to be I plus alpha I. So, what we do in the first parallel step is to copy every element of A into the corresponding into its corresponding element in C. In particular, AI is copied into C of I plus alpha I. Similarly, in the second step, the ith element of B will be copied into the I plus beta ith position of C. So, these two parallel steps each takes one unit of time. So, this part of the algorithm runs in order of 1 time, and the cross ranking part, as we have seen, runs in order of log n time, assuming that n is greater than or equal to m, using n plus m processors. So, the overall time complexity of the merge algorithm is order of log n using n plus m processors. As soon as we have an algorithm for merging, we can obtain a divide and conquer algorithm for sorting, which is called the merge sort. We shall see several variants of merge sort. This is the first of them. So, given an array A of size n, we need to sort A. So, the standard divide and conquer algorithm proceeds like this. Divide A into two equal halves. Sort each half recursively. And then merge the two halves. So, let us assume that we have n processors. And that our model is a CR-EWP-RAM. So, when we divide A into two equal halves, we will apportion the processors also accordingly. Half the processors will go to one problem instance and half the processors will go to the other problem instance. Then we will have two recursive invocations, each will have an array of size n by 2 with n by 2 processors, which is identical to the main invocation where we had n elements and n processors. The processor advantage is 1 in the recursive call as well. So, after solving the recursive instances, these two instances will be solved simultaneously, and then the two solutions will be combined by invoking the merge algorithm that we have just seen. The merge algorithm runs in order of log n time using n processors. In this case, the two arrays have exactly the same size. Therefore, the time complexity of the resultant sorting algorithm can be calculated using a recurrence relation. Let T of n denote the time required to sort n elements. So, what we have done is to divide the array into two equal halves and invoke the algorithm recursively on each half, but the two halves are running simultaneously. Therefore, the time taken will be T of n by 2 for the recursive calls. Since the two recursive calls are running simultaneously, we do not have to count their times separately. T of n by 2 does not have any multiplicative factor, and then merging them will take order of log n time. So, that becomes an additive term C times log n. So, this is the recurrence relation that governs the sorting algorithm. T of n equals to T of n by 2 plus C log n. So, let us see what is the solution for this recurrence relation. If you unroll the recurrence relation, we find that this is T of n by 4 plus C times log of n by 2 plus C times log of n. If we unroll once more, we get T of n by 8 plus C into log of n by 4 plus log of n by 2 plus log n. So, if you continue like this for k steps, the unrolled recurrence relation will look like this. If we put k equals log n minus 1, then the first term becomes T of 2, which is 1. Therefore, you can say this is T of 2 plus C times which is order of log squared of n. That is because the last term here is log n, the previous term is log n minus 1, then the second term from the right end is log n minus 2 and so on. So, when we add this sequence log n minus 1, log n minus 2 etc., all the way down to 2, the sum is going to be order of log squared of n. So, the sorting algorithm runs in order of log squared n time using n processors. So, now we have seen that on a CR EWP RAM, sorting of n elements takes order of log squared n time using n processors. This is not an optimal algorithm because the cost is order of n log squared n. Which is a log n factor off from optimality. An algorithm will be optimal only if the cost is order of n log n, which matches the time complexity of the sequential merge sort. We shall see later an algorithm which sorts optimally. So, we have now seen a sorting algorithm which runs in order of log squared n time, which in turn uses a merging algorithm that runs in order of log n time both on CR EWP RAM. Now, let us see how to design a merge algorithm that is optimal. The model is the same, CR EWP RAM. We shall use n plus m divided by log n number of processors to merge two sorted arrays of size n and m respectively in order of log n time, where n is greater than or equal to m. Therefore, the cost of the algorithm will be order of n plus m, the number of processors into the time taken. Therefore, the algorithm will be optimal. So, this will be a divide and conquer algorithm, which in turn uses the previous algorithm as a subroutine. So, given two sorted arrays A and B, what we do is this: the arrays A and B would both be divided into segments of size log n each. Therefore, we will have n by log n segments from one array and m by log n segments from the other array. In the first step, we divide the two sorted arrays into segments of size log n each. There will be n by log n segments from one array and m by log n segments from the other array. And then from each segment, we pick the first element as a special element. We select this element out of each array. These elements which occupy the first position of a segment are called the leaders. So, we have m plus n divided by log n leaders. The number of leaders is exactly equal to the number of processors we have. Let us say A prime is the array of leaders from A. Similarly, B prime is the array of leaders from B. The next step is to cross rank A prime and B prime using the available number of processors. Since the number of processors is exactly equal to the total size of A prime and B prime, we can use the previous algorithm that we have seen. That algorithm works when the total number of processors is exactly equal to the total size of the arrays. So, using that algorithm, we cross rank A prime and B prime. Let us say R1 of I is the rank of A prime of I, the ith leader of A in B prime. Similarly, R2 of I is the rank of B prime of I in A prime. So, now after the cross ranking is done, each leader of A prime knows two leaders on the other side between which it falls. Similarly, each leader in B prime knows two leaders in A prime between which it falls. In other words, each leader on either side knows the segment on the other side in which it belongs. So, let us consider the two arrays A and B. Consider a leader in A, let me call that leader X. The leader X knows the segment in B in which it falls. In particular, if this segment is the one from which the ith leader has been taken, that is, this is the ith leader, x knows that it is between the ith leader and the I plus first leader of B. The number of elements between these two leaders in B is log n. We have assumed that we have exactly as many processors as there are leaders. So, if you depute one processor to X, this processor can go to this segment within B to which X belongs and search the segment sequentially. The processor at X searches the segment sequentially to see where X fits. That is in sorted order, where would X fit? So, this would give us the rank of X in B. So, this can be computed by every single X in parallel in order of log n time. That is because we have assumed that every leader has one processor. This processor can go to the segment on the other side to which the leader X belongs and search within the segment sequentially. Since the length of the segment is log n, the sequential search will come to an end in order of log n time, even if we use a linear search. Therefore, in log n time, we would have ensured that every leader would be ranked in the other array. Let me define R1 of I as the rank of I, rank of A prime of I, the ith leader on the A side in B. R2 of I, capital R2 of I, is the rank of B prime of I, the ith leader of B in A. Now, consider the two lead arrays. Let me draw the two arrays with the leaders facing each other. The figure looks like two combs kept with the teeth facing each other. Now, what we have known is that for every single leader, it has found its rank in the other array. So, let us say the first leader on this side has found its rank like this, the second leader finds its rank here, then naturally the second leader on the other side will have to be ranked between these two because of the sorted order. What we find is that because of the sorted order, if we add pointers in this fashion, the pointers will never cross each other. In particular, if I consider a leader X on the lower side, so let the lower side be A and let the upper side be B. If X prime is the next leader in sorted order, whether it be from the same side or the other side, then if we consider the reflections of these two leaders, what I mean by reflection is the position at which it would fall in the other array, the rank of these two leaders. If I consider the reflections of these two leaders, I can take all the elements falling between these reflections, and I can also consider the elements that fall between X and X prime. These elements we find, the elements that are circled in blue, we find are strictly between X and X prime, and these elements are all larger than every element appearing to the left of these blue circles and are smaller than every element appearing to the right of these blue circles in the two respective arrays. Therefore, if the elements belonging to these are merged, these two circled arrays are subarrays of already sorted arrays, therefore, they are sorted subarrays. So, what we have is a subinstance of merging corresponding to the leader X. When we combine these two, when we merge these two subarrays in sorted order, and place them in the exact location where they should be in the final array, and this is done in parallel for every single leader, the problem would be solved. But then how do we know where these elements should go? The elements obtained by merging the two blue circles will have all these elements less than them, and these elements would also be less than them. We know the total number of elements marked in green, that will be where the result of the merge should go in the output array. So, once every single leader calculates the offset at which its result should go, then all that we have to do is to solve the individual merge instances in parallel and write the outputs in the exact place in the output array. So, the original merge problem now breaks down into several recursive problems. Originally we assumed that we have as many processors as there are elements. So, if these processors are distributed one per element, then for every recursive instance again we would have exactly as many processors as there are elements in the recursive instance. So, the recursive problem instances can be invoked exactly the same way this call has been invoked, with an equal number of processors to the problem size. Now, let us see what could be the maximum problem size of the recursive instances. My mistake, these are not recursive instances. An algorithm which uses a recursive invocation we shall see later. In this we will not be using recursion. So, the sub instances will have a size of order of log n at the most. We can argue this in this fashion. Consider two leaders on the A side. It could be that both the leaders rank into the same segment on the other side, in which case the number of elements between A and B in its own array would be log n, because that is the size of a segment. But the number of elements between A and B from the other array would be at most log n. Therefore, the total problem size can never exceed 2 log n in this case. That is, if two consecutive leaders on the same side rank within the same segment on the other side. On the other hand, if two consecutive leaders on the A side are not ranking into the same segment on the other side, let us say the first leader ranks here, but the second leader ranks in another segment. Therefore, this leader, the right leader on the B side, will have to be ranked between the two leaders on the A side. Therefore, the two consecutive leaders, if this is x, the nearest leader of x would be this one, y. Therefore, the number of elements between x and y would be the total number here plus the total number here. So, as you can see, this is at most log n, and this is also at most log n. Therefore, the total number of elements in the problem instance is going to be order log n again, which means all the sub instances can be solved in order of log n time, and then when they are copied into the exact place, the entire array will be sorted as well. So, what would be the boundaries of the sub instances? We will have two cases. consider the ith leader and the I plus first leader on the A side. Suppose both of them rank into the same segment on the other side. Then for the problem instance which is circled here, the left and right boundaries can be written like this: by AA left, let me name the first element on the A side going into the subinstance. Since the first element of every segment is picked out as a leader, the rank of this element within A would be I minus 1 into L plus 1, where L is log n, the length of a segment. This is because this element is the ith leader of A, which means it is the first element of the ith segment. Therefore, prior to this element there are I minus 1 full segments within A. They will contribute a total of I minus 1 into L elements, and then comes this element. Therefore, this is the I minus 1 into L plus first element within A, and the problem instance of which this element is in charge, this leader is in charge, is going to start from this element on the A side. Therefore, we call this AA left. The first A is because we are considering a leader on the A side. Then what I call AB left, if the rank of the leftmost element of the circle part on the other side, that is the B side, that would then be R1 of I plus 1. By the definition of R1, we know that R1 of I is the rank of I in B, that is the number of elements less than or equal to I in B. For now, we assume that all elements are distinct. So, if all elements are distinct, then the leftmost element within the circle part in B would be of index R1 of I plus 1 on the B side. Similarly, AA right would be the index of the rightmost element within the circle part on the A side. This would be I into L. That is because in this case it happens to be the I plus first leader on the A side. It is an element just before the I plus first leader on the A side. Therefore, its rank is going to be I into L. The last element within the circle part on the right side is going to have a rank of I into L on the A side. Similarly, on the B side, the last element within the circle part is the last element that is less than or equal to the I plus first leader of A. Therefore, it is going to have a rank of R1 of I plus 1. So, that was the first case. In the second case, again we consider two consecutive leaders on the A side, the ith leader and the I plus first leader. Let us say both of them do not fall within the same segment on the other side. Then there is a leader between them on the other side. Consider the leftmost such leader and consider the reflection of that leader on the A side. So, the elements that the ith leader of A are in charge of would be the circled elements. So, let us consider the boundaries of these circled elements. Let me define AA left and AB left as before. AA left you find this as before I minus 1 into L plus 1, because the leftmost element is a leader in the circle part of A. Similarly, AB right is R1 of I plus 1. But pardon me, AB left, that was AB left. AB right in this case is different from the previous case. In this case we find that this is R1 of I into L. AB right is the rightmost element on the B side within the circle part. This is going to be an element just before a leader, but then which leader would that be? We have to consider the number of leaders before the ith leader of A. The ith leader of A has small r1 of I leaders less than or equal to that on the B side. Now we are considering the next leader here, and the reflection of that is going to be the right boundary. So the element immediately before that will be the R1 of I into Lth element. That will be the rank of the rightmost element within the circle part on the B side. And finally we can calculate AA right in this fashion. AA right would be R2 of R1 of I plus 1. We want to calculate the index of this element within A. The leader, this leader is the R1 of I plus first leader on the B side. The rank of that within A is given by R2 invoked on that, which is what the rank of the rightmost element within the circle part in A is going to be. So these will define the boundaries of the problem in the second case. So putting all together, we can now look at the code of the algorithm. So here we have an algorithm for merging two arrays. We have two sorted arrays of sizes n and m respectively, capital N and capital M. Let us assume that capital N is greater than or equal to capital M. Then we define L as log of m into n. Mind you, logarithm of m into n is the same as log m plus log n, which is going to be order of log n when n is greater than or equal to m. So we are planning to divide the array into segments of size L. Let small n be the number of segments on the A side, and let small m be the number of segments on the B side. Then in parallel, from the two arrays we pick out the leaders and populate A prime and B prime. A prime will consist of the first elements from every segment of A, and B prime will consist of the first elements from every segment of B. And then we cross rank the leaders. Let R1 and R2 be the cross ranks. Now every leader on the A side knows its segment within the other side. Now in parallel, for every leader on the A side, we search for that leader on the other side. So A prime of I is searched for within the corresponding segment in B, and R1 of I minus 1 into L is the offset, which is to be added to the result of the search. That will give us the rank of A prime of I in B. That is what is going to be R1 of I. In an exactly analogous manner, we also calculate R2 of I. Now what remains is to calculate the problem boundaries. We calculate AA left, AB left, AA right and AB right, exactly the way we have mentioned now. The other four values, BB left, BA left, BB right and BA right, for the elements of B will be calculated analogously. For the leaders of B will be calculated analogously. So once we have the boundaries of the problems, we can invoke the sequential merge algorithm for the subproblems. That is, we merge the elements that fall between AA left of I and AA right of I on the A side, and AB left of I and AB right of I on the B side, and put those elements in their appropriate places within C, which will be AA left of I plus AB left of I minus 1 to AA right of I plus AB right of I. That is where these elements should go. So from the A left, A right, AB left, AB right values, we can calculate the exact places where the elements should go within the array C. Similarly, we do this for every single element of B as well. So, combining all of them, what we find is that the algorithm runs in order of log n time. Let us do a recap to see if the algorithm indeed runs in order of log n time. Picking out of the leaders will take only order 1 time, assuming that we have exactly as many processors as there are leaders. So, these two steps will run in order of 1 time each. Cross ranking will take order of log n time. Since we have exactly as many processors as there are elements in the arrays. And then these searches, these are sequential searches, this would take order of log n time again. These are sequential searches because we are using one processor for these searches. And then calculating of the boundaries will take order 1 time. All these calculations are done in parallel for every single processor. And then finally, we merge the sub instances sequentially, each will take order of log n time. Here we do in parallel for every single element on the A side, every single leader on the A side. Similarly, here we do this for every single leader on the B side, which would again take order of log n time. Since every leader is operating in parallel, the time taken is order of log n. And concurrent read has been used in multiple places, but concurrent write has not been used anywhere. So, the overall time complexity of the algorithm is order of log n, and we have used n plus m by log n processors. And the model used is the CR-EWP RAM. In the next lecture, we shall see how to improve the time complexity of the algorithm from order of log n to order of double log n, which is a substantial improvement on the same model. That will again be another divide and conquer algorithm. So, that is it. Hope to see you in the next.